Hello everyone, welcome back to my channel. So for today's video, I'm going to talk about water network synthesis. It's basically a process or technique that people use to minimize water, to recycle water, or to reuse water. And to demonstrate this, I'm going to use a process of converting scrap tires into fuel, just as a case study. I'm going to divide this video into two parts. The first part here is where I'm going to show you how to create a water pinch diagram. And on the second part of the videos, I'm going to show you how to interpret those diagram and then convert them and 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 use that information to create a new water network. Like for example, how much water is being diverted from one unit to another unit, and then how much water is being reused, and then how much water and wastewater need to be supplied and discharged. So yeah, let's begin. Yeah, as usual, I'm gonna begin with a quick introduction. Water network synthesis often use water. They often use a water pinch analysis method. And water pinch analysis method is more or less they originates from the heat pinch analysis that I have covered many months ago. So if you haven't checked my videos on those, please check them out. But water pinch analysis is basically a process or a technique that people use to reduce water consumption, to reduce how much wastewater is being discharged to the environment, where basically we have a stream that probably has a little bit of impurities, but it is good enough to be recycled, and then how much water that need to be recycled from one unit to another unit, and then how each recycled stream is distributed, and things like that. And of course, because this water pinch analysis obviously is being used in the processes that consume a lot of water. For example, here we have semiconductor industries, paper mill industries, palm oil industries, refinery and food industries. These industries use a lot of waters, and obviously they're gonna discharge a lot of wastewater as well. And of course, if you try to use a water pinch analysis, maybe we are able to recycle a lot of waters, and then we can recover a lot of waters and to be recycled back to supply water to the system or to the process as opposed of using fresh waters. So consequently, you have less water, wastewater discharge. So yeah, our task here is quite simple. It's very simple. We will perform water pinch analysis for tire to fuel processes. In short, in this process, scrap tires were used and they are converted using a pyrolysis process. It's basically a thermal process to form gaseous component as well as liquid fuel that can be used as a fuel, obviously. You can refer these references by Nuruddin and Al-Hawagi in 1999 if you want to know more details. But I don't want to go, I don't want to explain this too much. All right. So what would be our process flow? Process flow is quite simple. Here you have a tires. It goes to a water jet shredding where the big tires is being chopped into smaller pieces using a water jet. And of course, you're going to filter it where you have a cake and then solid. And of course, in here you have a fresh water supplied at 0.18 kilogram per second. In this process, undergoes compression and then recycled back to water jet shredding. And then this solid and then the broken down tires is undergo pyrolysis reactors, and then you have a gas, and then you also have maybe a remainder of the reactor product undergo a separation and so on and so forth. But I don't want to go details on the mechanics or the details on the process itself. But one thing that I want to highlight here is you have fresh water being supplied here, okay, labeled as a blue color, 0.18 kilogram per second. And then you also have a fresh water here supplied at the seal pot unit or area, if you will, at a flow rate of 0.10 kilogram per second. And then you also have water being discharged. Of course, this one is being It's hidden because I have my face in front, but it is a wastewater around 0.2 kilogram per second. And then Seaport also discharge a wastewater around 0.1 kilogram per second. Now, what we need to do here is we need to figure out how can we, is there a way for us to recycle this wastewater, you know, so that we can, number one, reduce the wastewater discharge and then reduce the freshwater intake and maybe use the freshwater wastewater to some of the process. But the question here is how. But one important thing that you should know is when you want to recycle something, you have to accept the fact that the recycled water is not really a clean water, it contains impurities. So you have to live with that. And then of course, but by that, we should also know that there's going to be some impurities being put back into your system because it is a recycled water. So in here, right? This is basically limiting water data for Tyre-to-Fuel case study. Of course, as I told you earlier, you have to accept the fact that when you recycle water, you have to accept that your water is not clean. It has some impurity, and a certain process may accept some impurities to a maximum value, to a maximum. They probably have an allowable impurity concentration that they can tolerate for a particular process. So in this case, right? Um, so what do we have here? So in here, right? We have a seed pot feed water. Basically, this one. What is the impurity allowable for them is 500 ppm. Means that fresh water is basically pure, right? Now for this particular stream, right? If you want to recycle to here, they allow impurity maximum of 500 or lower if you want. And then water jet make up basically this one make up water. They allow 50 ppm impurities into going into this particular area. Decanter wastewater, here is the impurity of your wastewater. Decanter wastewater is here. Uh, the wastewater in here is 500 ppm, and then the wastewater here is 200 ppm. So that's the whole process. Now, what do we need to do next? But before that, I just want to highlight, if you want to create a water pitch diagram, you have to remember two terms, all right? The first one is source. Source, by definition, is a stream that contain impurities, okay? That contain impurities, and they also contain the species that you want to recycle. You have to remember that. Now, simply say, okay, this is not the term, but I put it this way. It is an outlet of a process unit. Now, you have to remember outlet of a process unit is a lot, all right? But here I'm highlighting it is a terminal stream. Terminal stream here is basically you have outlet of a process stream, but it's not going to go, it doesn't go to the next process stream. If you know what I mean. It's basically go nowhere. It's ended. They don't go anywhere else. They just simply being discharged, things like that. So in the process, you see, there are stream going in, there are stream going out. But you have to remember, stream going out also goes to the next process stream. That one is not counted. Those are not source. Source is basically outlet of your process stream that contain the species that you want to recycle. But you also have to remember that it also contains impurities. But in here, the stream is terminal stream, means that it doesn't go to the next process unit. It just simply ended. Okay, simply say it's ended. Uh, Now, what are the important information that you should know from the source, right? Because if you have to recycle, you need to know what is your source, where's your recycle stream. Now, and then what is the flow rate? You need to know the flow rate. In here, they designate them as Fi. What is the impurity concentration? They designate as Ci. Okay, source is Ci. Impurity load is basically Mi. Actually, it was the other way around. It's J. I'm sorry here. This should be J. Fj, Cj, Mj, Fij. J multiplied by Cij. Okay. you have an impurity concentration. Impurity load is basically how much the flow rate of impurity. So it's a flow rate multiplied by concentration of whatever of the impurities in the source stream. Sink is much simpler definition. It is basically which process unit can receive the source. Okay, what is the process unit that can accept the recycled source? Yeah, it is exist by definition. It's existing process unit or equipment that can accept the source. Now in here you have a flow rate. You need to know the flow rate. You also need to know the impurity concentration, CJ. Actually, this sink people designate as CI. Uh, source people designate as J, or maybe the other way around, but doesn't really matter. These are the two terms that you should remember. Now, in here, you need to know flow rate, you also need to know concentration. But if you see here, CJ, the concentration here should be in between CJ minimum and CJ maximum. What does it mean here? As I told you, a process unit can tolerate a specific concentration. Maybe they allow for this level of impurities going into their process stream. Because why? You want to recycle water, right? The only way for you to recycle water is to match is into a certain process stream. It should be able to tolerate that certain impurities. And of course, the impurities cannot be too much, right? So they must have like a limit, lower limit and upper limit. But doesn't really matter. So those are the definition. Because why? These two definitions very important because later you need to identify what is your source and what is your sink. And lastly, here is load capacity is how much impurity flow rate, all right, that this process unit able to that process unit accept. Basically, it's a flow rate. It's a kilogram per second, time per second, kilogram per hour, whatever. But the how it's being calculated is basically the term is MI or MJ, if you will, is equal to FI, flow rate multiplied by concentration. So you have to remember there are two terms, sink and source. You have to remember those. Now, in here, how to solve this whole thing? Okay, first thing first, you need to identify step one. Step one, you need to identify your sink and source. And then you also need to determine their flow rate as well as impurity level. Now, sink here, as I mentioned earlier, is a process that that basically is a inlet. If you simply say it's an inlet, okay, going into the process stream. Now, in here, I have one sink going into this process unit. So I know its flow rate 0.1 kilogram per second, and then their impurities is let's see here 500. The second sink is a fresh water going into this particular process. Now the flow rate is 0.18, and then the impurities is let's see 50 ppm. Now those are your sink. How about your source? Source, as I mentioned earlier, it is a stream that contains that a species that you want to recycle. Obviously, it is an outlet of a process stream, but it doesn't go anywhere. As you can see, this doesn't go into the next process stream. It just ended. It is terminated. So obviously, I have a sink source number one having it's a wastewater 0.2 kilogram per second. And then I also have the second source, 0.1 kilogram per second. And then these are their impurities. So I have identified my sink and I have identified their source. I have identified their flow rate as well as impurity level. That's the first task. And as I mentioned earlier, this is not uh, okay, I just want to highlight here. This is not your what is it called? This is not your source because why? Even though this is an outlet of a process stream, but it goes to the next process stream. It is not terminated. So these are not your source. Your source should be it just ended that way. All right. Now, all right, the next step, the second step is basically you need to arrange your sink and source in ascending order of impurity level, and then you need to segregate the sink and source. I think the simplest way to do this is just to create this table. Just create this table where you have 1, 2, 3, 4, 5, 6, 7. You have a 7 column. I don't know whether you can see 7 column. The first column here is the stream name. The second one here is your designation. Is it a source or sink? Now, SK1, SK2 is basically its position. SK1 is the first row, SK2 second row, and so on and so forth. These are their flow rate. These are their impurity levels. As you can see here, impurity levels increasing order of impurity levels. It's getting dirtier, if you will. Now, the rest I'll show you later. Now, do the same for source. I designate them as R1, 2, and so on and so forth. If you have more than two streams, fluoride, their impurity levels, ascending order of impurity levels. So again, in these slides, create this table, 7 column, follow this, and then designate them as SK12, determine their flow rate, determine their impurity levels, and arrange your stream in increasing order of impurity levels. All right, and segregate the source and sink. That's basically the second step. We're still in the second step, but next we're going to continue calculating this part. MI here is impurity load. Basically, it's a flow rate of your impurities. How to calculate this? It's quite simple. As you can see, these are in milligram. You have to remember these are in milligram because my impurities is in ppm. Now, how to calculate this? Quite simple. For example, I give example here. How do I get 9? It's basically this multiplied by this. But actually, 0.18 kilogram per second multiplied by ppm is basically 1 ppm is 1 over 1 million, right? Now, 1 million, and then so divide by 1 over 1 million, right? So, and then you need to multiply it by the conversion. 1 million milligram multiply is equal to 1 kilogram. So million cancels out. So basically 0.18 times 50, you get 9 milligram per second. So this is 9 is basically this multiplied by this. 50 is basically this multiplied by this. 0.1 is basically this multiplied by this. No, 20 is basically 0.1 times 200. 100 is basically 0.2 multiplied by 5. It's quite simple, but have to check your unit. You have to be very careful. And for example, if you have a PPB, right, part per billion, or I don't know, something else, then you have to use a correct conversion factor. All right. Lastly, you need to calculate cumulative flow rate and cumulative impurity level for source, sink, and source. How to calculate is quite simple. This is 0 plus 18. Okay. Yeah, cumulative here is add Fij from preceding cell. So initially got 0. So 0 plus 0.18 is 0.18. Next is 0.18 times plus 0.1 is 0.28. Now here is 0 plus 9 is equal to 9. Now 9 plus 50 is equal to 59. Same goes with the third one is 0 plus 0.1 is 0.1. 0.1 plus 0.2 is 0.3. In here is 0 plus 20 is 20. 20 plus 100 is 120. It's very simple. Calculate this. Okay, the next step, this is step number 3. Step number 4, you're going to plot cumulative Fi and cumulative impurities, one curve, if you will. And then you do the same for the cumulative flow rate of source and cumulative impurities for sink. Put those two things in the same plot. Now you will get something like this. Now in here, I add one point, origin, 0, 0. Because these are for plotting, I put 0, 0. So that I have 0, 0 here, second point, third point, 0, 0, second point, third point. Now you can use Excel or whatever plotting software that you have to plot this, but as long as you get something like this, should be fine. Now this is step number 4. Now step number 5, you need to shift this plot. All right, you need to shift this plot so that this plot becomes kind of a tangent, I would say. Basically, they move until one of the curve of the red one touches the blue one. So you need to shift the red one. Now, how to shift? So when you shift, the origin is no longer 0, 0. So in here, I have to shift 0.135. So when I shift from here to here 0.135, you need to add here 0.135. You also need to add here 0.135. So the rest are the same. Now I get this point connected, touches one of these line. It cannot be like a 2 points, it should be 1 point. And lastly, you have this kind of curve where this point touches the one of the source stream, and this is the fifth step. Where this is the fifth step where you're gonna come up with this final, I'll say, plot. But and then you will need to analyze your plot and interpret the values and then translate them into a new water, I'll say, network or process stream network for recovery and recycling, which we will try to do next week. Right. That will be all for me. I hope you like the videos. If you haven't subscribed, please subscribe to my videos. And as I mentioned earlier, part two of the videos will come up maybe next week and or maybe in 10 days. All right. Stay tuned and have a very nice day.